the geometry of space. Is the universe flat, curved, or something stranger? Right now, as you listen to this, you are sitting still. At least, that is what your senses are telling you. But the truth is far more unsettling. You are riding on a planet spinning at over 1,000 miles per hour, orbiting a star at 67,000 miles per hour, which itself is hurtling through a galaxy, moving at 1.3 million miles per hour through the cosmos. And all of that motion, every single mile per hour of it, is happening on a stage whose very shape we are not entirely sure of. Here is the question that should keep you up at night. Imagine you could fire two laser beams into the void of space, perfectly parallel to each other. You aim them with impossible precision so that they start exactly 1 meter apart, and you let them fly. In the geometry you learned in school, those beams would stay 1 meter apart forever. They would never touch, never drift, never converge. But what if the universe does not play by those rules? What if, after traveling for billions of light years, those two beams slowly, imperceptibly, began to drift toward each other and eventually crossed? Or what if they drifted apart, separating further and further until the gap between them became an uncrossable chasm? The answer to what happens to those two beams of light tells us something extraordinary. It tells us the shape of the entire universe, not the shape of galaxies, not the shape of planets, the shape of space itself, the invisible, intangible fabric upon which every atom, every star, every thought you have ever had exists. And for most of human history, nobody even thought to ask the question, because for over 2,000 years, humanity operated under one simple, elegant, and deeply incomplete assumption: that space was flat, that the geometry of the cosmos was the same geometry you doodled in your notebook in middle school, that parallel lines stay parallel, that the angles of a triangle add up to 180 degrees, and that the shortest distance between 2 points is a straight line. It took a chain of geniuses, misfits, and rebels working across centuries and continents to shatter that assumption. And what they discovered was not merely that the universe might be curved. They discovered that the question itself, the question of the geometry of space, is one of the most profound questions a conscious being can ask. Because the geometry of the universe does not just describe the shape of space, it determines the fate of everything in it. Whether the cosmos will expand forever into cold darkness, or collapse back on itself in a fiery implosion, or drift along some strange middle path that no one fully understands, all of it depends on the answer to one question: is the universe flat, curved, or something stranger? This is that story, a story that spans 2,300 years of human thought, from the sunlit columns of ancient Alexandria to the freezing darkness of Antarctic balloon flights, from the scratching of quill pens on papyrus to the terabytes of data streaming from satellites orbiting 1,000,000 miles from Earth. It is a story of geniuses who were ignored, discoveries that were suppressed, and ideas so radical that the men who conceived them were afraid to publish. And it is a story that is still being written today, because the answer, as you will see, is far from settled. To understand the geometry of the universe, we need to go back, way back, to a city on the Mediterranean coast of Egypt, roughly 2,300 years ago. The city of Alexandria was, at that time, the intellectual center of the ancient world. Its great library held hundreds of thousands of scrolls. Scholars from across the Greek-speaking world gathered there to debate, to teach, and to write. Ships arrived daily at its harbor, carrying papyrus, spices, and ideas. The city hummed with the energy of discovery. And among those scholars was a man whose work would dominate human thought for longer than any empire, any religion, any political system in history. His name was Euclid. We know almost nothing about Euclid as a person. We do not know when exactly he was born or when he died. We do not know what he looked like, whether he was tall or short, or whether he preferred wine or water. We barely know anything about his personality, except for one famous anecdote in which a student allegedly asked him what practical use geometry had. And Euclid supposedly told a servant to give the student a coin, since he clearly needed to profit from what he learned. Whether the story is true or not, it captures something essential about Euclid's worldview. Geometry, to him, was not about practicality. It was about truth, pure, crystalline, eternal truth. Around 300 BC, Euclid compiled a work called The Elements. It was not a single flash of inspiration. It was a monumental act of organization. Euclid gathered the accumulated geometric knowledge of the Greek world, everything from Pythagoras to Eudoxus to Theaetetus, and structured it into a logical system unlike anything that had existed before. He started with a handful of definitions, a few common notions, and 5 postulates, statements he assumed to be true without proof. From those bare bones, he built an entire edifice of geometric knowledge. 13 books, 465 propositions. A cathedral of logic, constructed one theorem at a time, each one resting on the ones that came before. The Elements would become the most influential mathematics textbook in human history. It was studied without interruption for over 2,000 years. Abraham Lincoln taught himself logic by reading it, keeping a copy in his saddlebag as a young lawyer riding the Illinois Circuit. It was the second most printed book in the Western world for centuries, trailing only the Bible. Baruch Spinoza modeled his ethics on its structure. Thomas Hobbes, upon first encountering a proof in the Elements at the age of 40, was reportedly so astonished that he exclaimed an oath and worked backward through the chain of reasoning, theorem by theorem, all the way to the postulates. Isaac Newton structured his Principia Mathematica to echo the Elements, building his physics from axioms just as Euclid had built his geometry. The Elements was not merely a book. It was a template for rational thought itself, the method of starting with simple, self-evident assumptions and building toward complex conclusions through airtight logical proof became the model for inquiry, not just in mathematics, but in philosophy, science, law, and theology. For 2 millennia, to think rigorously was to think like Euclid. And at the foundation of this immense edifice were just 5 postulates, 5 assumptions taken as given from which everything else followed. The first 4 were almost comically simple. The 5th was anything but. The first 4 postulates were, to put it simply, obvious. The first said that you can draw a straight line between any 2 points. The second said you can extend that line as far as you want. The third said you can draw a circle with any center and any radius. The fourth said that all right angles are equal. These were the kind of assumptions that felt self-evident, the kind of thing you would nod along to without a second thought. They were simple, clean, and intuitive. But the 5th postulate was different. The 5th postulate, which became known as the parallel postulate, was worded in a way that felt clunky, awkward, almost suspicious. Here is what it says, translated into modern language. If a straight line crosses 2 other straight lines, and the interior angles on one side add up to less than 180 degrees, then those two lines will eventually meet on that side if you extend them far enough. In other words, lines that are not parallel will eventually intersect. Now, this sounds reasonable enough, but compared to the crisp elegance of the first four postulates, the fifth felt like it was doing too much work. It was too complicated, too wordy, too much like a theorem in disguise. It had an if-then structure that made it feel derived, not fundamental. And Euclid himself seemed to sense this. He managed to prove his first 28 propositions without ever invoking the fifth postulate. It was not until proposition 29 that he finally had to reach for it, and you can almost feel his reluctance in doing so. And that hesitation, that subtle unease, planted a seed that would take over 2,000 years to bloom. For century after century, mathematician after mathematician tried to prove the fifth postulate from the first four. They attacked it from every conceivable angle, with every tool available to them. The Greek philosopher Proclus tried in the 5th century, living and working in Athens during the twilight of the classical world. Proclus wrote an extensive commentary on Book 1 of the Elements, and in it, he noted that the parallel postulate seemed less certain than the others. He attempted a proof of his own, but it was circular. He had smuggled in an assumption that was logically equivalent to the very thing he was trying to prove. The torch passed to the Islamic world, where mathematics flourished during Europe's intellectual dormancy. The Persian polymath Omar Khayyam, better known today for his Rubaiyat poems about wine and roses and the fleeting nature of life, was also a brilliant mathematician. In the late 11th century, Khayyam explored what would happen if the fifth postulate were false. He considered a quadrilateral with two right angles and examined three possibilities for the remaining angles: right, acute, or obtuse. He derived results in the acute and obtuse cases that were perfectly consistent, results that belonged to geometries he could not yet name. But he believed these alternatives must be wrong, and he argued, on philosophical grounds rather than mathematical ones, that the Euclidean case was the only valid one. Nasir al-Din al-Tusi, working in the 13th century, made another attempt. Al-Tusi was a Persian scholar of extraordinary range, a mathematician, astronomer, philosopher, and theologian who had survived the Mongol conquest of Baghdad and found patronage with the conquerors. His critique of the parallel postulate was detailed and sophisticated, but ultimately, his proof also rested on an assumption equivalent to the postulate itself. In Europe, the Italian Jesuit priest Girolamo Saccari published a book in 1733 with the wonderfully optimistic title Euclid's Ab Omni Nivo Vindicatus, meaning Euclid freed of every flaw. It remains one of the great ironic titles in mathematical history, because Saccari's book, far from vindicating Euclid, actually laid the groundwork for his overthrow. Saccari spent years constructing elaborate logical chains, hoping to derive a contradiction that would prove the fifth postulate must be true. He considered a quadrilateral with two right angles and investigated what happened if the remaining two angles were obtuse or acute. He quickly dispatched the obtuse case by finding a contradiction, but the acute case proved stubbornly resistant. Saccari pushed deeper and deeper into the mathematics, deriving result after result, filling page after page, and still no contradiction appeared. He had, without realizing it, built an extensive body of theorems in what we now call hyperbolic geometry. But in the end, he declared his results were repugnant to the nature of a straight line, and pronounced the fifth postulate proved. He was wrong, But his failure was more productive than he could have imagined. The German mathematician Johann Heinrich Lambert took it even further. Working in the 1760s, Lambert explored what would happen if the fifth postulate were replaced with its negation. He discovered formulas for the area of triangles in this hypothetical geometry. And he noticed that these formulas resembled the formulas for the area of triangles on a sphere. He even speculated that non-Euclidean geometry might be realized on the surface of an imaginary sphere, a sphere with an imaginary radius. Lambert came tantalizingly close to the truth, closer than anyone before him. But he died in 1777 without publishing his work, and the manuscript was not printed until years after his death. And so, for over 2,000 years, the fifth postulate stood, unproven, unshaken, a crack in the foundation of geometry that nobody could seal, and nobody could widen far enough to see through. It was the longest-running unsolved problem in mathematics, and its resolution would come not from one genius, but from three, working independently in 3 different countries at almost exactly the same time. The first was Carl Friedrich Gauss, born in 1777 in the German city of Brunswick, to a working-class family, his father a bricklayer and gardener, his mother an illiterate maidservant. Gauss was, by any measure, one of the greatest mathematicians who ever lived. He was a prodigy of almost terrifying ability, the kind of mind that appears perhaps once in a century. At the age of 3, according to a story his mother liked to tell for the rest of her life, he corrected an arithmetic error in his father's payroll calculations. His father, totaling up a column of figures after a long day of work, had gotten the wrong answer. The toddler, listening from across the room, piped up with the correct one. By the age of 7, Gauss astonished his schoolteacher with a feat of mental arithmetic that has become one of the most famous anecdotes in the history of mathematics. The teacher, hoping to keep the class occupied, assigned the students the task of adding up all the integers from 1 to 100. Most children dutifully began the laborious process of adding 1 plus 2 plus 3, and so on. Gauss, within seconds, placed his slate on the teacher's desk with the correct answer, 5,050. He had realized in a flash of insight that the numbers could be paired. 1 and 100 make 101. 2 and 99 make 101. 3 and 98 make 101. And so on, for 50 pairs. 50 times 100, and 1 is 5,050. It was a trivial observation to a mathematician, but for a 7-year-old to see it instantly, without prompting, was extraordinary. By the time he was a teenager, he was making discoveries that would have been the crowning achievement of most mathematicians' entire careers. At 19, he proved that a regular 17-sided polygon could be constructed with a compass and straightedge, a result that had eluded mathematicians for 2,000 years. He later described this discovery as the moment he decided to devote his life to mathematics. Gauss began thinking about the foundations of geometry in the 1790s. While still a young man, he was troubled, as so many before him had been, by the fifth postulate. But unlike his predecessors, Gauss did not spend years trying to prove it. Instead, he slowly, carefully, over the course of years of private reflection, arrived at a stunning conclusion. The fifth postulate could not be proved because it was not necessarily true. There existed a perfectly consistent, perfectly logical geometry in which the fifth postulate was false, a geometry in which through a given point, you could draw not just one line parallel to a given line, but infinitely many. A geometry in which the angles of a triangle add up to less than 180 degrees. A geometry that was, as Gauss himself coined the term, non-Euclidean. But Gauss, for all his brilliance, was cautious to the point of secrecy. He was a perfectionist who released his results to the world only when they were polished to a mirror sheen, and he had an additional reason for caution in this case. He genuinely feared the reaction of his peers. In an 1824 letter to a colleague named Franz Torinus, Gauss laid out his ideas in a tantalizing outline, but implored Torinus to keep them private. He worried that if he published the Boeotians, his contemptuous term for the less gifted members of the mathematical community, would attack him. He did not wish to waste his precious time engaging in pointless arguments with people who could never fully understand what he had found. Gauss's reluctance meant that the honor of first publication fell to two other men, each working in isolation, each unaware of the other. The first was Nikolai Lobachevsky, born in 1792 in the Russian city of Nizhny Novgorod. Lobachevsky spent his entire professional life at the University of Kazan, a city on the Volga River deep in the Russian interior, far from the mathematical capitals of Europe. The intellectual distance was even greater than the geographical one. Lobachevsky had little access to the latest European research and almost no means of publicizing his own, but he was brilliant, tenacious, and unafraid of radical ideas. In 1829, Lobachevsky published a paper in the Kazan Messenger, a small local journal with almost no international circulation, describing what he called imaginary geometry. It was a bold and lonely act. Lobachevsky had no assurance that anyone would read it, let alone understand it. The paper described a fully worked-out geometry in which, through a point knot on a given line, there were infinitely many lines that would never intersect the original. Triangles had angles adding up to less than 180 degrees, and the deficit grew with the size of the triangle. Small triangles, ones you might draw on a desktop, looked Euclidean essentially. The differences were undetectable at small scales. But large triangles, ones spanning cosmic distances, became increasingly alien, their angle sums dropping further and further below the familiar 180. Lobachevsky understood the implications of his work. He was not merely solving a mathematical puzzle. He was showing that the geometry of physical space was an empirical question, not a logical certainty. In his later writings, he even proposed an astronomical experiment to test whether the geometry of the universe was Euclidean or not. By measuring the angles of a triangle formed by distant stars, the measurements available in his time were not precise enough to detect any deviation from Euclidean geometry. But the idea itself was revolutionary. It anticipated, by nearly a century, the methods that modern cosmologists would use to measure the curvature of space. Lobachevsky spent the rest of his life trying to get his work recognized, publishing in French, German, and Russian, hoping to reach the mathematical centers of Western Europe. The response was largely indifference or hostility. One reviewer described his work as mathematical nonsense. He received medals from the Russian government, but for his administrative work as rector of the university, not for his mathematics. In one of history's more ironic footnotes, one of his last government citations was not for revolutionizing geometry, but for inventing a new method of processing wool. Lobachevsky died in 1856, nearly blind and largely forgotten, without ever knowing that he had helped shatter a 2,000-year-old monopoly on truth. The second independent discoverer was János Bolyai, a Hungarian military officer and mathematician born in 1802. His father, Farkas Bolyai, was himself a mathematician who had spent frustrating years wrestling with the parallel postulate and had become convinced that the problem was a kind of intellectual trap, beautiful but ultimately destructive. When Farkas learned that his son had taken up the same obsession, he wrote a desperate, almost pleading letter. The parallel postulate, the elder Bolyai warned, was a dark, bottomless abyss. It could devour a man's entire life. "For God's sake," he wrote, "I beseech you, give it up. Fear it no less than sensual passions, because it, too, may take all your time and deprive you of your health, peace of mind, and happiness in life." János did not listen. By 1823, working as a military engineer in the Austrian army, he had developed the foundations of a non-Euclidean geometry. He wrote excitedly to his father, "Out of nothing I have created a strange new universe." In 1832, his results were published as a 26-page appendix to one of his father's books. Overjoyed, Farkas immediately sent the work to his old friend Gauss, hoping that the great man would recognize his son's genius. Gauss's reply landed like a blow. He wrote back that he could not praise the work, because doing so would amount to praising himself. He claimed to have arrived at the same conclusions years earlier, though he had never published. The Bolyais were crushed. Farkas felt his friend had betrayed his son. János suspected plagiarism. Neither charge was fair. Gauss had genuinely developed similar ideas in private, as his letters and notebooks would later confirm. But the damage was done. János Bolyai retreated from mathematics. He never published another significant work. He spent the remaining decades of his life in relative obscurity, nursing a bitterness that never fully healed. He died in 1860, at the age of 57, without learning of Lobachevsky's parallel discovery on the other side of Europe. These three men, Gauss, Lobachevsky, and Bolyai, working independently across Europe, had collectively shattered the most enduring assumption in the history of mathematics. They had shown that Euclid's geometry was not the only geometry. It was not a necessary truth. It was one possibility among several. The parallel postulate was not a theorem waiting to be proved. It was a choice, and different choices led to different geometries, each one internally consistent, each one a valid description of some conceivable kind of space. But the discovery of non-Euclidean geometry raised a question even more profound than the one it answered. If there are multiple valid geometries, which one describes the real world? Which geometry governs the space we actually live in? Answering that would require a mind that could see beyond any specific geometry to the abstract structure that unifies them all. It would require Bernhard Riemann. On June 10, 1854, in a lecture hall at the University of Göttingen in Germany, a shy, nervous young mathematician stood before a small audience and delivered a talk that would change the course of human civilization. His name was Georg Friedrich Bernhard Riemann. He was 27 years old. He was terrified of public speaking, and he was about to redefine the meaning of space itself. Riemann had been born in 1826, the son of a Lutheran pastor in a small village in what is now northern Germany. He was the second of 6 children, and the family was poor. His father taught him at home until the age of 10, and young Bernhard showed an early gift for mathematics, though he was painfully shy around people. When he was 14, his school principal lent him a copy of a famous mathematics textbook by Adrian Marie Legendre. The book was 859 pages long. Riemann returned it after 6 days, saying he had read it all and found it wonderful. When tested on its contents, he demonstrated a complete mastery of every proof. Riemann attended the University of Göttingen, initially intending to study theology to support his family. But the pull of mathematics was too strong. He transferred to mathematics, studying under some of the greatest minds of the era, and eventually returned to Göttingen to pursue his habilitation, the degree that would allow him to become a lecturer. The habilitation process required a public lecture on a topic chosen by the candidate's advisor. Riemann prepared 3 possible topics and submitted them to his doctoral advisor for selection. His advisor was none other than Carl Friedrich Gauss, now 77 years old, a monumental figure in the last year of his life. 2 of Riemann's proposed topics were safe, conventional choices about electricity and mathematical physics. The third, on the foundations of geometry, was risky and speculative, a topic Riemann feared he had not fully prepared. Gauss, to Riemann's alarm, chose the third. Riemann spent months in intense preparation. He was so anxious that he could barely eat or sleep. But when the day came, what emerged was one of the most astonishing intellectual achievements in human history. In less than an hour, Riemann laid the groundwork for an entirely new way of thinking about space, one that would eventually provide the mathematical language for Einstein's general theory of relativity. The lecture was titled On the Hypotheses Which Lie at the Foundations of Geometry, and its central argument was revolutionary. Riemann proposed that geometry was not a fixed property of space. It was a variable. Space could be curved in different ways, at different places, at different times. And the rules of geometry, the behavior of lines and angles and distances, depended entirely on the curvature of the space you happened to be in. To make this precise, Riemann introduced the concept of what he called a manifold, a mathematical space that could have any number of dimensions and any kind of curvature, but that locally, in sufficiently small regions, looked like ordinary flat space. Think of the surface of the Earth. If you stand in a meadow, the ground seems flat. The horizon stretches in a line. Triangles you draw on the grass obey all the rules of Euclidean geometry. But zoom out, keep zooming, and the flatness dissolves into the unmistakable curve of a sphere. The surface of the Earth is a two-dimensional manifold, locally flat, globally curved. Riemann generalized this idea to spaces of any number of dimensions. A three-dimensional space could be curved, just like a two-dimensional surface. So could a four-dimensional space, or a 10-dimensional one. And crucially, the curvature did not have to be the same everywhere. It could vary from point to point, just as the curvature of a mountain landscape varies from the peak to the valley to the saddle between two hills. To describe this variable curvature, Riemann introduced a mathematical object now called the Riemannian metric, sometimes called the metric tensor. It is a collection of numbers at every point in space that tells you how to measure distances and angles in the neighborhood of that point. In 2 dimensions, you need 3 numbers at each point. In 3 dimensions, you need 6. In 4 dimensions, the number Riemann showed was needed is 10. The metric encodes everything there is to know about the geometry of the space: its curvature, its shape, its stretching and squeezing, the way it bends light and alters distances. Think of it this way. Imagine you are a tiny creature living on an unknown surface. You cannot see the surface from the outside. You cannot lift yourself above it. All you can do is move along it, measure distances, and draw triangles. If you measure a small triangle and find that its angles add up to exactly 180 degrees, you might conclude you are on a flat plane. But if you measure a much larger triangle and find the angles add up to more than 180 degrees, you would know, without ever leaving the surface, that you are on something like a sphere. And if the angles add up to less than 180 degrees, you are on something shaped like a saddle. The metric tells you how to make these measurements. It is the complete geometric DNA of the space, encoding every curve, every twist, every stretch in a compact mathematical form. Riemann went further. He showed that a single number, the Gaussian curvature that his teacher had defined for surfaces, was not sufficient to describe curvature in higher dimensions. In 3 dimensions, you need 6 independent numbers at each point. In 4 dimensions, you need 20. These numbers form what is now called the Riemann curvature tensor, a mathematical object of considerable complexity but extraordinary power. It tells you everything about how a space curves and bends, not just in one direction, but in every direction simultaneously. And Riemann did not stop at mathematics. At the end of his lecture, he made a remarkable philosophical suggestion. He proposed that the geometry of physical space might not be given in advance. It might be determined by physical forces. The metric of space, the thing that governs distances and angles, might be influenced by the matter and energy present in the space. In other words, the geometry of the universe might be a physical quantity, not a mathematical axiom. This was a staggering idea, decades ahead of its time, and it would find its full expression only when Einstein built his theory of gravity. Gauss, sitting in the audience, was deeply moved. He had spent decades developing the theory of curvature for 2-dimensional surfaces. And here was his student, extending those ideas into territories Gauss himself had only dimly perceived. According to those who were present, Gauss was visibly excited, speaking with unusual animation after the lecture about the depth and originality of Riemann's ideas. It was one of the last great mathematical moments of Gauss's extraordinary life. He would die less than a year later, in February of 1855, carrying with him the satisfaction of having set Riemann on this path. Riemann himself did not live long enough to see the full impact of his work. Always frail, he contracted tuberculosis and spent his final years seeking relief in the warm climate of Italy. He died on July 20th, 1866, at the age of 39, in a small village overlooking Lake Maggiore. His lecture was not published until 1868, 2 years after his death, but when it finally appeared, it sparked a revolution in mathematics and, eventually, in physics. Albert Einstein, reflecting on Riemann's contribution decades later, wrote with evident awe about how Riemann had anticipated the geometric framework that Einstein himself needed to describe gravity. Einstein once remarked that only Riemann's genius, solitary and uncomprehended, had already won its way by the middle of the 19th century to a new conception of space, one in which space was deprived of its rigidity, and its power to participate in physical events was recognized as possible. And indeed, it was Einstein who would take Riemann's abstract mathematics and turn it into a physical theory of the universe. Albert Einstein did not start out thinking about geometry. He started out thinking about light. In 1905, while working as a patent clerk in Bern, Switzerland, he published his special theory of relativity, which showed that measurements of space and time depend on the observer's motion. A clock moving at high speed ticks more slowly. A ruler moving at high speed contracts along its direction of motion. These were not optical illusions or mechanical effects. They were fundamental properties of the universe. Space and time were not the rigid, absolute containers that Isaac Newton had imagined. They were flexible, relative, and deeply entangled with each other. Einstein's former professor, Hermann Minkowski, took this insight and gave it a powerful geometric interpretation. In a famous lecture in 1908, at a meeting of the German Association of Scientists and Physicians, Minkowski declared, in words that would echo through the history of physics, that henceforth, space by itself and time by itself were doomed to fade away into mere shadows, and that only a union of the two would preserve an independent reality. It was a dramatic pronouncement, almost theatrical in its sweep, and it annoyed Einstein, who felt his teacher was dressing up simple physics in unnecessary mathematical finery. He proposed that space and time should be thought of not as separate entities, but as a single, unified, four-dimensional structure. Space-time. Every event in the universe, every moment, and every location could be described as a point in this four-dimensional space-time. The path of a particle was not a trajectory through three-dimensional space accompanied by a separate ticking clock. It was a single curve through the four-dimensional landscape. Einstein initially dismissed Minkowski's geometric reformulation as, in his words, superfluous learnedness. He saw it as an unnecessary mathematical complication. But he would soon learn from his former teacher one final time, because Einstein had a problem, a big one. Special relativity described a universe without gravity. It worked beautifully for objects moving at constant velocities in empty space. But the real universe was full of matter, full of mass, full of gravitational pull, and incorporating gravity into relativity turned out to be the hardest intellectual challenge Einstein ever faced. He wrestled with it for a full decade, from 1905 to 1915. The struggle was grueling, a marathon of false starts, dead ends, and near misses that tested Einstein's intellect and his emotional resilience. He later described those years as the most intense intellectual effort of his life, a period during which he felt he was groping in the dark, never certain he was on the right path. The difficulty was fundamental. In Newton's physics, gravity was a force that acted instantaneously across space. The sun pulled the earth pulled the moon, and the gravitational influence traveled at infinite speed. But special relativity had abolished the idea of instantaneous action. Nothing could travel faster than light. So how could gravity be transmitted? Einstein explored one approach after another. He tried to modify Newton's gravitational law to be compatible with special relativity. He considered scalar theories, vector theories, and tensor theories. He made errors that led to years of wasted effort. At one point in 1912, he developed a set of field equations that were almost correct, but he rejected them because he mistakenly believed they did not reduce to Newton's gravity in the appropriate limit. He would not rediscover the correct equations for 3 more years. The breakthrough came through geometry. Einstein's friend and collaborator Marcel Grossmann, a mathematician, introduced him to the work of Riemann, and to the subsequent development of tensor calculus by Gregorio Ricci-Bastro and Tullio Levi-Civita. These tools, abstract and unfamiliar to most physicists of the time, turned out to be exactly what Einstein needed. They allowed him to express the curvature of spacetime in a precise mathematical form, and to write equations relating that curvature to the distribution of matter and energy. In the autumn of 1915, working feverishly and racing against the great mathematician David Hilbert, who was pursuing the same goal by different methods, Einstein finally found the correct field equations. On November 25, 1915, he presented them to the Prussian Academy of Sciences. The equations were elegant, powerful, and startlingly concise. They would reshape humanity's understanding of gravity, space, time, and the cosmos. The key insight, when it finally came, was breathtaking in its simplicity and depth. Einstein realized that gravity was not a force in the traditional Newtonian sense. It was a consequence of geometry. The presence of mass and energy caused spacetime itself to curve, to warp, to bend. And objects moving through that curved spacetime followed the straightest possible paths, which mathematicians call geodesics. These paths appeared, from the perspective of someone standing on the surface of a planet, to be curved by a gravitational force. But in reality, the objects were moving in straight lines through curved space. There was no force at all, only geometry. A planet orbiting a star was not being pulled by an invisible rope. It was simply following the curvature of spacetime created by the star's mass. The Earth was not being attracted to the Sun. It was rolling along the curved geometry of spacetime, like a marble rolling along the inside of a bowl. To express this mathematically, Einstein needed exactly the tools that Riemann had created 60 years earlier. He needed the metric tensor to describe the curvature of four-dimensional spacetime. He needed the mathematical machinery of differential geometry to relate the distribution of matter and energy to the curvature of spacetime. The result was his general theory of relativity, published in November 1915, embodied in a set of equations now called the Einstein field equations. They are among the most beautiful and successful equations in all of physics. On one side of the equation sits the Einstein tensor, a mathematical object describing the curvature of spacetime. On the other side sits the stress-energy tensor, describing the distribution of matter and energy. The equation says that these two things are equal, or more precisely, proportional. Curvature equals content. Geometry equals physics. The predictions of general relativity were extraordinary and, at first, difficult to believe. The theory predicted that light should be bent by gravity, its path curving as it passes near a massive object. This was confirmed during a total solar eclipse in 1919, when Arthur Eddington measured the deflection of starlight by the sun, finding it matched Einstein's predictions. The news made front pages around the world and transformed Einstein from a respected physicist into a global celebrity. The theory predicted the existence of gravitational waves, ripples in the fabric of spacetime produced by accelerating masses. These waves were finally detected 100 years later, in September of 2015, by the LIGO Observatory, when two black holes spiraling into each other produced spacetime vibrations that stretched and squeezed the 4-kilometer-long detector arms by a distance smaller than the width of a proton. The discovery earned the 2017 Nobel Prize in Physics. The theory predicted black holes, regions of spacetime so severely curved that nothing, not even light, can escape. Einstein himself doubted that black holes could actually exist in nature, but observations over the following decades proved him wrong. In 2019, the Event Horizon Telescope collaboration produced the first direct image of a black hole's shadow, a dark void surrounded by a glowing ring of superheated gas, exactly as general relativity predicted. And the theory predicted something even grander than any of these individual phenomena. It predicted that the geometry of the entire universe, the curvature of space on the largest possible scales, is determined by the total amount of matter and energy the universe contains. The physicist John Wheeler would later capture the essence of general relativity in a single memorable sentence. Matter tells space how to curve, and space tells matter how to move. This simple statement contains an entire universe of physics. It describes the orbits of planets, the bending of light around stars, the existence of black holes, the expansion of the universe, and the propagation of gravitational waves across the cosmos. And here is where the story turns cosmic. Because if the geometry of spacetime is shaped by matter and energy, then the geometry of the entire universe depends on how much matter and energy it contains. The shape of the universe is not fixed, not a given, not written into the fabric of reality from the beginning. It is a consequence of what the universe is made of. It is a physical quantity, something that can be measured, something that evolves over time. Einstein himself was the first to apply his equations to the universe as a whole. In a landmark paper published in 1917, just 2 years after unveiling general relativity, he assumed that matter was spread uniformly throughout space, the simplest possible arrangement, and cranked through the calculations. What he found disturbed him deeply. His equations did not describe a static universe. They described a universe in motion, either expanding or contracting. This was unacceptable to Einstein. Like virtually every scientist of his era, he believed the universe was eternal and unchanging. The idea of a cosmos with a beginning, or an end, or even a direction of change, seemed almost philosophically absurd. And so Einstein made what he would later call his greatest blunder. He added a term to his equations, a fudge factor called the cosmological constant, represented by the Greek letter lambda. This constant was designed to counterbalance the attractive pull of gravity, holding the universe still. With just the right value of lambda, Einstein could produce a static, spherical, finite universe with positive curvature, a universe that fit his philosophical preferences. It was a Russian mathematician and meteorologist who showed Einstein that his philosophical preferences were wrong. Alexander Friedmann was born in 1888 in St. Petersburg, Russia. He was a man of remarkable range and courage. He studied mathematics and physics at the university there, and during World War I, he served in the Russian Imperial Army as a pilot, flying reconnaissance and bombing missions over the Austrian front. Between missions, he worked out mathematical models of bomb trajectories and then tested them during actual flights. He was not a theorist who worked in the safety of a study. He was a man who put his equations to the test from the cockpit of an airplane. After the war, in the early 1920s, Friedmann turned his formidable mathematical ability to Einstein's equations, and in a paper published in June of 1922 in the prestigious German journal Zeitschrift für Physik, Friedmann did something that Einstein had been unwilling to do. He let go of the assumption that the universe was static. He simply took the equations, assumed the universe was homogeneous and isotropic, and solved them. The solutions were spectacular. Friedman found that the universe was dynamic, depending on the values of various parameters, including the density of matter and the cosmological constant. The universe could expand forever, or it could expand and then contract in an endless cycle, or it could reach a maximum size and then collapse back to a point. In no natural scenario did the universe remain still. Einstein initially rejected Friedman's work. He sent a note to the journal claiming that Friedman had made a mathematical error, but Friedman wrote back with painstaking politeness and rigorous detail, showing that the error was not his, but Einstein's. Einstein eventually published a brief correction acknowledging his mistake, though he still seemed unable to embrace the idea of a dynamic universe. It would take Edwin Hubble's observational discovery in 1929, showing that distant galaxies were receding from us at speeds proportional to their distances, to convince the world that the universe was indeed expanding. Exactly as Friedman's mathematics had predicted, Friedman's solutions also revealed something profound about the connection between the content of the universe and its geometry. His equations contained a parameter describing the spatial curvature, and that parameter could take one of three values, each corresponding to a fundamentally different kind of universe. If the density of matter and energy in the universe exceeded a critical threshold, the curvature was positive. The universe curved back on itself, like the three-dimensional analog of the surface of a sphere. Such a universe was finite in volume, but had no edges, no boundaries. You could travel in a straight line forever and eventually return to your starting point. The angles of a large enough triangle would add up to more than 180 degrees. Two beams of light fired in parallel would eventually converge and cross. This was a closed universe. If the density fell below the critical threshold, the curvature was negative. The universe curved outward like the three-dimensional analog of a saddle. Such a universe was infinite in extent and would expand forever. Triangles had angles adding up to less than 180 degrees. Parallel beams of light would slowly diverge. This was an open universe, and if the density was exactly equal to the critical threshold, the curvature was precisely zero. The universe was flat. It had the familiar geometry of Euclid, stretching out in perfect, infinite, uncurved spaciousness. Parallel lines remained parallel forever. This was the flat universe, balanced on a knife's edge between the other two. Cosmologists defined a parameter called omega, the ratio of the actual density of the universe to the critical density. If omega was greater than 1, the universe was closed. If the omega was less than 1, it was open. If omega was exactly 1, it was flat. The critical density itself, the dividing line, worked out to something astonishingly sparse, roughly 6 hydrogen atoms per cubic meter. That is not a misprint. The difference between a universe that collapses in fire and one that expands forever into cold darkness comes down to the equivalent of a handful of hydrogen atoms sprinkled across a space the size of a large closet. To appreciate how strange this is, think about what each scenario means for the history and fate of the cosmos. In a closed universe, the expansion that began with the Big Bang would gradually slow, then stop, then reverse. Galaxies that had been flying apart for billions of years would begin drifting back together. The universe would contract, growing hotter and denser. The cosmic microwave background blue shifting from microwaves back to visible light, then to ultraviolet, then to X-rays. Stars would be engulfed by the encroaching heat. Eventually, all the matter and energy in the cosmos would be compressed back into an unimaginably hot, dense state. A big crunch, a mirror image of the Big Bang. In an open universe, the opposite would happen. The expansion would never stop, never even slow to zero. Galaxies would fly apart faster and faster, the distances between them growing without limit. Stars would burn through their nuclear fuel and die. White dwarfs would cool to black dwarfs. Neutron stars would fade. Black holes would grow, consuming whatever stray matter they could find, before themselves slowly evaporating through Hawking radiation over timescales that make the current age of the universe look like the blink of an eye. The universe would grow darker, colder, emptier, stretching toward an infinite, frigid void. And in a flat universe, the expansion would slow, approaching zero asymptotically, but never quite stopping. It would be a middle path, the cosmic equivalent of a ball thrown upward at exactly escape velocity. It never falls back, but it never truly gets away. The fate would be similar to the open case, an endless cooling and dimming, but at a more measured pace. The geometry of the universe, in Friedman's framework, is not an abstract mathematical curiosity. It is a prophecy. It tells us how the universe was born, how it evolved, and how it will end. Friedman did not live to see his equations vindicated. He died in 1925 at the age of 37, from typhoid fever contracted during a high-altitude balloon flight. But his work endures as one of the foundational pillars of modern cosmology. The Friedman equations, as they are now universally known, describe the evolution and geometry of the universe with a precision and elegance that has only deepened with time. So there were three possible shapes, three geometries, three destinies for the cosmos. But how could we possibly figure out which one was real? The universe is incomprehensibly vast. We cannot step outside it and look at its shape from the outside, any more than an ant crawling on a balloon can see that the balloon is round. We are imprisoned within the universe, limited to observations we can make from the inside. But here is the beautiful thing. You do not need to step outside a curved space to detect its curvature. You can measure it from within. Just as a sufficiently clever ant on a balloon could, in principle, discover the curvature of its world by measuring triangles and tracking the behavior of parallel lines, we can discover the curvature of the universe by making careful measurements of very distant things. And the most useful distant thing we have ever found, the most powerful tool for measuring the geometry of the cosmos, is the oldest light in the universe, the cosmic microwave background. The story of the cosmic microwave background begins at the very beginning, at the moment of creation itself. In the first moments after the Big Bang, roughly 13.8 billion years ago, the universe was unimaginably hot and dense. The temperature in the first second was measured in billions of degrees. Space was filled with a ferocious soup of elementary particles, quarks, electrons, neutrinos, and photons, all smashing into each other with tremendous energy. There were no atoms. There were no molecules. The temperature was far too high for anything so complex to survive. As the universe expanded and cooled, the quarks combined into protons and neutrons, and some of those protons and neutrons fused into the nuclei of the lightest elements, hydrogen, helium, and trace amounts of lithium. This process, called Big Bang nucleosynthesis, occurred in the first few minutes. But even then, the universe was still too hot for atoms. The electrons remained free, whizzing around in a sea of charged plasma, and the photons could not travel far without smashing into those free electrons. The universe was opaque, like the interior of a star. Light was trapped, bouncing from electron to electron, unable to escape. Imagine trying to see through the heart of the sun. You cannot, because the solar interior is a dense plasma where photons are constantly absorbed and re-emitted, bouncing around in a random walk that can take hundreds of thousands of years before a photon finally reaches the surface and escapes. The early universe was like that everywhere. The entire cosmos was a fog, but the universe was expanding, and as it expanded, it cooled. 380,000 years after the Big Bang, the temperature dropped to about 3,000 degrees Kelvin, a critical threshold. At that temperature, protons and electrons finally had low enough energy to combine into neutral hydrogen atoms. Physicists call this moment recombination. And recombination was a watershed event, because neutral atoms do not scatter photons the way free charged particles do. Suddenly, the universe became transparent. Light could travel freely for the first time. Photons that had been trapped in the plasma were suddenly released, streaming outward in all directions. Those photons have been traveling through space ever since. For 13.8 billion years, they have been crossing the cosmos. And during that time, the expansion of the universe has stretched their wavelength enormously. What began as energetic visible light has been redshifted all the way down into the microwave portion of the electromagnetic spectrum. Today, this radiation fills the entire universe, arriving from every direction in the sky. Its temperature is a mere 2.725 degrees above absolute zero. It is the cosmic microwave background, the CMB, and it is arguably the single most important observation in all of cosmology. The CMB was first detected in 1964 by Arno Penzias and Robert Wilson, two radio astronomers at the Crawford Hill facility of Bell Telephone Laboratories in Holmdel, New Jersey. They had built a highly sensitive radio antenna, originally designed for satellite communication experiments. A large horn-shaped device, about 20 feet across, that had been used to receive signals bounced off the Echo balloon satellites. When Penzias and Wilson repurposed it for radio astronomy, they found a persistent, mysterious hiss of microwave static that they could not eliminate. The noise was everywhere. It was the same intensity no matter where they pointed the antenna. Whether toward the bright band of the Milky Way or the dark voids between galaxies, whether during the day or at night, whether in summer or winter, they checked every possible source of interference. They examined the antenna for electrical faults. They tightened every bolt. They discovered that a pair of pigeons had been nesting inside the antenna horn, coating it with what Penzias delicately referred to as a white dielectric material. They trapped the pigeons, drove them to a site 30 miles away, and released them. The pigeons, as pigeons do, flew straight back. Penzias and Wilson ultimately had to resort to more permanent measures. But even after the pigeons and their deposits were removed, the hiss remained. It was not until Penzias happened to mention the problem to a colleague who knew of theoretical work being done at nearby Princeton University by Robert Dicke and James Peebles that the mystery was solved. Dicke and Peebles had been predicting exactly such a background radiation as a leftover from the early universe. When Dick received the phone call telling him about the Bell Labs detection, he reportedly turned to his colleagues and said, "Boys, we've been scooped." What Penzias and Wilson had stumbled upon was the afterglow of the Big Bang itself. They had detected the cosmic microwave background, the ancient light released at the moment the universe became transparent, now cooled and stretched to microwave wavelengths by 13.8 billion years of cosmic expansion. For their discovery, they were awarded the Nobel Prize in Physics in 1978. It remains one of the most serendipitous discoveries in the history of science, a case of two engineers solving one of the deepest questions in cosmology while trying to fix what they thought was a hardware problem. The CMB is not perfectly uniform. It is almost perfectly uniform, the same temperature in every direction to 1 part in 100,000. But those tiny variations, those subtle fluctuations of a few millionths of a degree from one patch of sky to another, encode a wealth of information about the physics of the early universe. They are the imprints of density variations in the primordial plasma, tiny regions where the matter was slightly denser or slightly less dense than average. These density variations were the seeds from which all the structure in the universe would eventually grow. The first stars, the first galaxies, the vast filaments and clusters of the cosmic web, and ultimately, the planets, the oceans, and the living creatures that would one day look up at the sky and wonder what shape it was. In the early universe, these density variations were not static. They were alive with motion. Regions of higher density attracted more matter through gravity, compressing the plasma and heating it up. But the enormous pressure of the tightly packed photons pushed back against the compression, creating outward-moving waves. The result was a phenomenon almost poetic in its beauty. Sound waves rippling through the primordial plasma, not sound in the ordinary sense, of course. There was no air to vibrate, no ear to hear. But the physics was the same. Alternating regions of compression and rarefaction, of heat and cold, of density and void, rippled outward from every dense seed at a speed determined by the temperature and composition of the plasma, roughly 57% of the speed of light. These cosmic sound waves played for 380,000 years, the entire duration of the universe's opaque era. When recombination occurred, and the universe became transparent, the sound waves froze in place, like a drumhead suddenly silenced in mid-vibration. The pattern of compressions and rarefactions at that moment was imprinted onto the CMB as a pattern of hot and cold spots. Hotter where the plasma was compressed, cooler where it was rarefied, and those spots have a characteristic size determined by the sound horizon. The maximum distance a sound wave could have traveled in 380,000 years. The physics of the early universe determines exactly how far sound waves could travel in the first 380,000 years. That distance, the sound horizon, is calculable from first principles. It is about 143,000 parsecs, or roughly 467,000 light-years. This is the known physical size of the most prominent fluctuations in the CMB. It is a cosmic ruler, and here is where geometry becomes measurable. The apparent angular size of an object depends on the geometry of the space between you and the object. In flat space, objects appear exactly the size you would predict based on their distance. In a positively curved space, light rays converge, making distant objects appear larger than expected. In a negatively curved space, light rays diverge, making distant objects appear smaller. So by comparing the known physical size of the CMB fluctuations with their observed angular size in the sky, cosmologists can directly measure the curvature of space. It is, in essence, a cosmic triangle test. You have a ruler of known length, the sound horizon, sitting at a known distance, the surface of last scattering roughly 13.8 billion light-years away. You measure the angle that the ruler subtends in the sky, and the geometry of the space between you and the ruler determines what angle you see. If the universe is flat, the angle comes out to about 1 degree. If the universe is positively curved, like a sphere, the light rays converge, and the spots in the CMB appear larger, so the angle is bigger than 1 degree. If the universe is negatively curved, like a saddle, the light rays diverge, and the spots appear smaller, so the angle is less than 1 degree. It is elegant, powerful, and remarkably direct, a method for weighing the geometry of the entire cosmos using the faint whisper of ancient light. But making this measurement is fiendishly difficult in practice. The fluctuations in the CMB are tiny, just millionths of a degree. Extracting their pattern requires instruments of extraordinary sensitivity, placed in environments where atmospheric interference is minimized, and combined with sophisticated data analysis techniques that can separate the cosmological signal from the many sources of noise. The glow of our own galaxy, the contaminating radiation of interstellar dust, the thermal emission of the instrument itself, and the subtle electronic artifacts of the detectors. The first experiment to do this with high precision was BOOM, RAN-G, an acronym for Balloon Observations of Millimetric Extragalactic Radiation and Geophysics. It was led by Andrew Lange of Caltech and Paolo de Bernardis of the University of Rome La Sapienza. The concept was ingenious. Rather than build a satellite, which would cost billions, they would carry a telescope to the edge of space using a high-altitude balloon. The balloon was launched from McMurdo Station in Antarctica in December of 1998 and floated at an altitude of over 42,000 meters for 10.5 days, circling the Antarctic continent on the polar vortex, while the telescope scanned the sky with bolometric detectors cooled to less than 1/3 of a degree above absolute zero. The results, announced in April of 2000, electrified the physics community. The angular size of the dominant fluctuations in the CMB was almost exactly 1 degree, precisely the value predicted for a flat universe. The density parameter omega was measured to be 1.0, plus or minus about 12%. The universe, as far as BOOM RAN-G could tell, was flat. A competing experiment called Maxima, also using a balloon-borne telescope, confirmed the result at even finer angular resolution. The convergence of these independent measurements was powerful evidence. But 12% uncertainty left room for doubt. The universe could still have been slightly open or slightly closed within those error bars. What was needed was a dedicated space mission that could map the entire sky with even greater precision. Within a few years, that mission arrived. NASA launched the Wilkinson Microwave Anisotropy Probe, known as WMAP, in June of 2001, named in honor of the late cosmologist David Wilkinson, who had been one of the pioneers of CMB measurement. WMAP was sent to the second Lagrange point, a gravitationally stable location about 1.5 million kilometers from Earth, where the Sun, Earth, and Moon all lie in roughly the same direction. From there, The satellite could observe the full sky without interference, spinning slowly to build up a complete map of the microwave heavens. Over 9 years of operation, it produced what NASA described as a baby picture of the universe, the most detailed map of the CMB ever made at the time. WMAP pinned down the curvature of space to within 0.4% of flat. It measured the age of the universe to be 13.77 billion years, with an uncertainty of less than 0.5%. It was determined that ordinary atoms make up about 5% of the universe, dark matter about 25%, and dark energy about 70%. Then came the European Space Agency's Planck satellite, launched in May of 2009. Planck was even more sensitive than WMAP, observing the CMB at higher resolution and across more frequency bands. Its results, released in 2013 and refined in subsequent years, confirmed the flatness of the universe with extraordinary precision. The total density parameter omega was measured to be 1.000, plus or minus just 0.004. As far as our most sensitive instruments could determine, the universe was flat. Perfectly, exactly, puzzlingly flat. The flatness of the universe is not just an interesting fact. It is deeply, almost suspiciously, strange. And the reason it is strange requires understanding how cosmic geometry evolves over time. In Friedmann's equations, the curvature of the universe is not fixed. It changes as the universe expands, and it changes in a very specific, very troubling way. Any deviation from perfect flatness gets amplified. If the universe starts out even slightly denser than the critical density, the positive curvature grows, and the universe becomes increasingly curved, eventually collapsing. If it starts out even slightly less dense, the negative curvature grows, and the universe becomes increasingly open. Flatness is an unstable equilibrium. Imagine balancing a pencil on its tip. Push it even slightly to one side, and it topples. The universe's flatness is like that pencil. For it to still be balanced after 13.8 billion years of cosmic evolution, it had to be extraordinarily precisely balanced at the very beginning. Working backward from the present-day observations, physicists calculated that at just 1 second after the Big Bang, the density of the universe had to be equal to the critical density, to an accuracy of 15 decimal places. That is 1 part in a million billion. To grasp how extreme this is, imagine trying to balance a coin on its edge, on a table, on a ship, in a storm. Except the odds are vastly worse than that. If the density had been larger by even the tiniest conceivable fraction, the universe would have collapsed under its own gravity long before any stars could form. If it had been smaller by the same infinitesimal amount, the expansion would have been so rapid that matter would have been flung apart before it could ever coalesce into galaxies. The universe as we know it, with its stars and planets and people, exists only because the initial density was tuned to an accuracy that makes the word precision seem laughably inadequate. And if you go back further, to even earlier times, the fine-tuning gets worse. At the Planck time, roughly 10 to the negative 43 seconds after the Big Bang, the epoch when quantum gravitational effects are expected to be important, the density had to be tuned to 1 part in 10 to the 60th power. That is a 1 followed by 60 zeros. There is no known physical principle in standard Big Bang cosmology that could explain such outrageous precision. This was the flatness problem, and it gnawed at cosmologists for years. The standard Big Bang theory had no explanation for it. It simply had to assume that the initial conditions were exactly right, without providing any mechanism to make them so. The theory worked beautifully, but only if you fed it initial conditions that seemed arbitrary and unnatural. The answer, when it came, was both elegant and mind-bending. It originated not in cosmology, but in particle physics. In the fall of 1978, a young postdoctoral physicist named Alan Guth attended a lecture at Cornell University by the astronomer Robert Dicke. Dicke was a legendary figure in experimental physics, a Princeton professor who had helped develop the techniques for measuring the cosmic microwave background, and who had a deep intuitive feel for the most pressing problems in cosmology. He described the flatness problem in stark, compelling terms, explaining how the density of the universe had to be tuned with absurd precision at early times to produce the nearly flat cosmos we observe today. Guth was captivated. He had been working on problems in grand unified theories, the ambitious attempts to merge the strong, weak, and electromagnetic forces into a single framework. But Dicke's lecture opened his eyes to a deep connection between particle physics and cosmology, between the physics of the infinitely small and the physics of the infinitely large. Over the following year, Guth worked on the magnetic monopole problem, a separate cosmological headache arising from grand unified theories. These theories predicted that the early universe should have been filled with extremely massive magnetic monopoles, hypothetical particles with an isolated north or south magnetic pole, but not a single monopole had ever been observed. Where were they? On the night of December 6, 1979, working alone in his office at the Stanford Linear Accelerator Center, Guth had what he later described as a spectacular realization. He actually wrote those words in his notebook, in block capital letters, with a box drawn around them. He had realized that a particular type of quantum field transition in the very early universe, a transition that could solve the monopole problem, would also solve the flatness problem and the horizon problem in a single stroke. If a quantum field, now called the inflaton, had been temporarily stuck in a high-energy state, a state known as a false vacuum, it would have generated an enormous, repulsive gravitational force, causing the universe to expand exponentially, not at the steady pace described by Friedmann's equations, but at a staggering, explosive rate, doubling in size every inconceivably tiny fraction of a second. This period of exponential expansion, which Guth called inflation, would have lasted only from about 10 to the negative 35th seconds to 10 to the negative 33rd seconds after the Big Bang, an interval so brief that it defies human comprehension. To put this in perspective, the entire duration of inflation was shorter than the time it takes light to cross the diameter of a proton, divided by 1 trillion. It was an event of almost zero duration, and yet during that vanishingly brief flicker, the universe would have grown by a factor of at least 10 to the 26th, and possibly far, far more. A region smaller than an atom would have been inflated to a volume larger than the entire observable universe. Distances that had been submicroscopic were stretched to cosmic proportions in less time than it takes the blink of an eye to begin. The mechanism behind inflation is rooted in quantum field theory. Guth proposed that a quantum field, now called the inflaton field, had been temporarily trapped in a high-energy configuration known as a false vacuum. In quantum field theory, the vacuum is not truly empty. It is the lowest energy state of a field. But sometimes, a field can get stuck in a local minimum of energy that is not the true minimum, like a ball resting in a shallow dip on a hillside rather than at the bottom of the valley. This false vacuum state has an extraordinary property. It generates a negative pressure that, in the context of general relativity, produces a repulsive gravitational effect. Instead of pulling matter together, it pushes space apart, and it does so exponentially. Eventually, the inflattened field decayed from its false vacuum state to its true vacuum state, releasing an enormous amount of energy. That energy reheated the universe, filling it with the hot plasma of particles and radiation that we associate with the Big Bang. In a very real sense, inflation was the bang in the Big Bang. The hot, dense, expanding universe that we observe did not start from a singularity in the way physicists once imagined. It started from the decay of the inflattened field at the end of inflation, and inflation solved the flatness problem in one magnificent stroke. The mechanism is simple and intuitive. Think of the surface of a balloon. When the balloon is small, its curvature is obvious. You can easily see that it is round, but inflate it to the size of the Earth, and any small region of its surface is indistinguishable from a flat plane. Blow it up to the size of the solar system, and the curvature becomes vanishingly small. Now imagine inflating it to a size trillions of times larger than that. Whatever curvature it started with, positive or negative, would be diluted to undetectability. The same principle applies to the universe. No matter what the initial curvature was, inflation stretched the universe so dramatically that the observable portion, the part we can see, was driven to extreme flatness. The curvature is still there, technically, somewhere far beyond the horizon of our observations. But within our observable universe, it is so close to zero that no instrument could detect the difference. In January of 1981, Guth published his paper titled Inflationary Universe, a possible solution to the horizon and flatness problems. It has since been cited tens of thousands of times and is a cornerstone of modern cosmological theory. But inflation did even more than solve the flatness problem. It also explained the horizon problem, the puzzle of why the CMB is so uniform across the entire sky. Without inflation, opposite sides of the observable universe would never have been in causal contact. There simply was not enough time since the Big Bang for a light signal to travel from one side to the other. So how could they have exactly the same temperature? Inflation answered this by proposing that everything we observe originated from a minuscule region, small enough for thermal equilibrium to be established, that was then inflated to cosmic proportions. And inflation made a sharp, testable prediction about geometry. It predicted that the universe should be flat, not approximately flat, not nearly flat, but flat to extraordinary precision. Because inflation drives the universe so powerfully toward flatness, the natural outcome is omega equal to exactly 1. That is, within our measurement uncertainties, exactly what we observe. But the cosmological narrative was about to take another dramatic turn, one that nobody anticipated, and that, even now, nobody fully understands. Through the 1990s, 2 teams of astronomers were racing to measure how the expansion of the universe was slowing down. Everyone expected it to be slowing. Gravity, the mutual attraction of all the matter in the cosmos, should have been gradually putting on the brakes, decelerating the expansion over time. The only question was how fast. To measure this deceleration, they used a particular type of exploding star called a Type 1a supernova. These are among the most spectacular and useful events in all of astronomy. A Type 1a supernova occurs in a binary star system where two stars orbit each other. One of the stars has already died and collapsed into a white dwarf, a dense remnant about the size of the Earth, but with a mass comparable to the Sun's. The white dwarf slowly siphons matter from its companion, growing more and more massive, until it reaches a critical threshold called the Chandrasekhar limit, roughly 1.4 times the mass of the Sun. At that point, the internal pressure can no longer support the star against its own gravity, and the entire white dwarf is consumed in a thermonuclear explosion of staggering power, briefly outshining its entire host galaxy. Because the detonation always occurs at approximately the same mass, these supernovae produce approximately the same peak luminosity. They are not perfectly identical, but a relationship between the brightness of the explosion and the rate at which it fades, discovered by the astronomer Mark Phillips in 1993, allows astronomers to calibrate the brightness to high accuracy. This makes Type 1a supernovae excellent standard candles, objects of known intrinsic brightness that can be used to measure distances. By comparing how bright a supernova appears to how bright it actually is, astronomers can calculate its distance, and by measuring the redshift of its host galaxy, they can determine how fast the galaxy is receding. Put the distance and the recession velocity together for many supernovae at different distances, and you can trace the history of cosmic expansion over billions of years. The two teams were the Supernova Cosmology Project, led by Saul Perlmutter, and the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees. They were competitors, working independently, using different telescopes and analysis techniques, but pursuing the same goal. In 1998, both teams announced results that were, frankly, shocking. The distant supernovae were not brighter than expected, as they would be if the expansion were decelerating. They were fainter. They were further away than any model with decelerating expansion could explain. The expansion of the universe was not slowing down. It was accelerating. The reaction within the physics community ranged from skepticism to astonishment. Brian Schmidt later recalled that, when the data first pointed toward acceleration, his initial response was that something must be wrong. Adam Rees wrote a computer program to calculate the mass of the universe from the supernova data, and the answer came back negative mass. He thought his code had a bug. He spent weeks checking and rechecking, convinced there was an error somewhere. There was not. The negative mass was not a mistake. It was a consequence of forcing a decelerating model onto data that demanded acceleration. Both teams checked for systematic errors obsessively. Could the distant supernovae be dimmed by intergalactic dust rather than by additional distance? They tested this and found no evidence for it. Could the supernovae at high redshift be fundamentally different from nearby ones, perhaps slightly less luminous? The spectral data argued against it. Could there be some unknown photon scattering process that would make distant objects look fainter? Nobody could find one. Explanation after explanation was examined and rejected. The conclusion, however uncomfortable, seemed inescapable. The expansion of the universe was speeding up. This was one of the most unexpected discoveries in the history of science. Something was pushing the universe apart, counteracting the attractive pull of gravity. Something was causing the expansion to speed up over time, like a ball thrown into the air that accelerates upward instead of falling back down. Scientists named this unknown agent dark energy. And when they measured its contribution to the total energy budget of the universe, they found it was not a minor player. Roughly 68% of the total energy content of the cosmos was dark energy. Another 27% was dark matter, a mysterious substance that interacts gravitationally but does not emit or absorb light. Ordinary matter, the familiar stuff of atoms and molecules, the stuff of which stars and planets and people are made, constituted a mere 5%. Perlmutter, Schmidt, and Rees shared the 2011 Nobel Prize in Physics for their discovery. It was named the Breakthrough of the Year by Science magazine in 1998, and it has remained one of the central puzzles of modern physics ever since. And it has profound implications for the geometry of the universe. Remember, the curvature of space depends on the total density of matter and energy. For decades, cosmologists had been trying to measure the density of the universe, counting up all the visible matter, estimating the dark matter from the rotation curves of galaxies and the dynamics of galaxy clusters, and consistently finding that the total came up short. The universe seemed to contain only about 30% of the critical density needed for flatness. If that were the whole story, the universe would be open, negatively curved, and expanding forever. But dark energy changed the equation entirely. When you add up all the components, ordinary matter at about 5% of the critical density, dark matter at about 27%, and dark energy at about 68%, the total comes to almost exactly 100% of the critical density. Omega equals 1. The universe is flat. Dark energy makes up the missing piece. It is the invisible counterweight that tips the cosmic scales to exactly the critical density. Without it, the geometry would be open. With it, the books balance to extraordinary precision. This is not a minor point. It is one of the most remarkable and least understood coincidences in all of physics, the fact that the total energy density of the universe, composed of 3 wildly different components with 3 completely different physical origins, adds up to almost exactly the value that produces a flat geometry. Dark energy, this incomprehensible substance whose nature we do not understand, provides exactly the amount needed to make the geometry of the universe Euclidean. Nobody knows what dark energy is. This is not an exaggeration for dramatic effect. It is a literal statement of the current state of physics. The most energetic, the most abundant, the most important component of the universe, the thing that makes up more than 2/3 of all the energy in the cosmos and determines its ultimate fate, is something we do not understand at all. The leading theoretical candidate for dark energy is the energy of empty space itself, which physicists call vacuum energy. In quantum field theory, the vacuum is not truly empty. It seethes with quantum fluctuations, virtual particles popping in and out of existence, in accordance with Heisenberg's uncertainty principle. These fluctuations carry energy, and that energy, in principle, could act as a cosmological constant, producing exactly the kind of repulsive gravitational effect that drives the accelerating expansion. But when physicists try to calculate the expected value of the vacuum energy from quantum field theory, the result is catastrophic. The predicted value is roughly 10 to 120th times larger than the observed value of dark energy. Let that number sink in for a moment. 10 to the 120th. That is a 1 followed by 120 zeros. It is not a small disagreement. It is not a factor of 2 discrepancy that could be resolved with a more careful calculation. It is the largest known discrepancy between theory and observation in the entire history of science. The physicist Steven Weinberg called it the worst prediction ever made. Some physicists have proposed that dark energy is not the cosmological constant at all, but rather a dynamical field that changes over time, a substance called quintessence. Others have suggested modifications to general relativity itself, theories in which gravity behaves differently on the largest scales, producing an apparent acceleration without the need for dark energy. Still others have explored the possibility that the acceleration is an illusion, a consequence of the fact that we happen to live in a region of the universe that is less dense than average, creating a bias in our measurements. None of these alternatives has been confirmed, and none has gained widespread acceptance. The truth is, we are in the dark about dark energy. It is the biggest unsolved problem in fundamental physics. What we do know is this: the combination of flat geometry and accelerating expansion paints a specific picture of the cosmic future. The universe will expand forever, faster and faster. Distant galaxies will be carried away from us beyond the reach of even light. The cosmic microwave background will be stretched to wavelengths too long to detect. Stars will burn through their fuel and die, one by one. Black holes will slowly evaporate through Hawking radiation. And eventually, after an inconceivable span of time, the universe will become a cold, dark, empty expanse, expanding into eternity, unless, of course, the geometry is not the whole story. Because there is something else, something that most people overlook when they hear that the universe is flat. Something that physicists themselves sometimes gloss over in popular accounts. Something that could mean the cosmos is far more interesting and far more bizarre than a simple flat sheet extending forever in all directions. When we say the universe is flat, we are making a statement about geometry, about the local rules governing lines and angles and distances. But geometry is only half the story. There is another property of space, equally fundamental, equally important, and far less constrained by our observations. It is called topology, and understanding the difference between geometry and topology opens the door to a range of possibilities for the shape of the universe that are as strange and wonderful as anything in science. Here is the thing that most people overlook when they hear that the universe is flat. Flatness tells you about the local geometry of space, the rules that govern how lines and angles and distances behave in small regions. But it tells you almost nothing about the global shape of space, the way space is connected to itself on the largest scales. That global property is called topology, and it is an entirely separate question from geometry. To understand the difference, consider a simple example. Take a flat sheet of paper. It is flat in the geometric sense. Now roll it into a cylinder. The cylinder is also geometrically flat. If you were a tiny, two-dimensional creature living on its surface, you would find that all the rules of Euclidean geometry hold perfectly. Triangles have angles summing to 180 degrees. Parallel lines stay parallel. The curvature is zero everywhere. But a flat sheet and a cylinder are topologically different. The sheet extends indefinitely in all directions. The cylinder is finite in one direction. Walk far enough around it, and you come back to where you started. The geometry is the same. The topology is different. Now take this one step further. Start with a flat rectangular sheet. Glue the top edge to the bottom edge to make a cylinder. Then glue the left edge to the right edge. What you get is a torus, a donut shape. And here is the remarkable part. A torus can be perfectly flat. There exists a flat torus. A creature living on a flat torus would experience Euclidean geometry in every local measurement. But the space would be finite. Walk far enough in any direction, and you arrive back where you began. It is like a video game screen where exiting the right edge brings you back on the left, and exiting the top brings you back at the bottom. Small, finite, but perfectly flat. This is not just mathematical amusement. It is a genuine possibility for our universe. The CMB measurements tell us that space has a flat or nearly flat geometry. But they do not tell us that space is infinite. A flat universe could be infinite, like an endless Euclidean plane stretching out forever in all directions. A space without boundaries, without edges, without limit. Or it could be finite, wrapped around on itself in some topological configuration that we have not yet detected. A space that is compact and closed, but still perfectly flat in its local geometry. The distinction matters enormously. An infinite universe and a finite universe with the same local geometry would look identical to any observer making measurements in a small region. They would have the same angles, the same distances, the same curvature. The difference would only become apparent if you could travel far enough or observe far enough to detect the wrapping. It is like the difference between an endless ocean and a lake that loops back on itself. From the perspective of a fish swimming in a small circle, they are indistinguishable. Mathematicians have cataloged the possibilities with meticulous care. For a three-dimensional space with flat geometry, there are exactly 18 possible topologies. 10 of them are finite and compact, meaning they have a definite volume. 6 of those are orientable, meaning they have a consistent notion of left and right. The simplest is the three-dimensional torus. The most complex involve twists and inversions that challenge even a trained mathematician's imagination. For curved spaces, the possibilities multiply further. A positively curved three-dimensional space could be a simple three-sphere, the three-dimensional analog of the surface of a ball, or it could be any one of an infinite family of more complex shapes, formed by identifying faces of polyhedra in various ways. In 2003, a team of cosmologists led by Jean-Pierre Luminet of the Paris Observatory proposed a specific, provocative model for the topology of the universe. They noticed an anomaly in the WMAP data. The very largest scale fluctuations in the CMB were weaker than expected. In an infinite flat universe, there should have been fluctuations on all scales, including the very largest, but the data showed a suppression. The biggest sound waves were missing, as if the universe were simply not big enough to support them. Luminet and his team proposed that the universe might have the shape of a Poincaré dodecahedral space. The idea is both simple in concept and mind-bending in execution. Imagine a regular dodecahedron, a 12-faced polyhedron where every face is a regular pentagon, one of the 5 Platonic solids. Now imagine identifying each pentagonal face with the opposite face, with a slight clockwise twist of 36 degrees. What this means is that if you were walking through this space and you reached one of the pentagonal boundaries, you would not hit a wall. You would seamlessly pass through and emerge from the opposite face, rotated by 36 degrees. It is as if the space is stitched to itself, each face connected to its opposite in a way that creates a closed, finite volume. The result is a three-dimensional space that is positively curved and compact. It has a finite volume, roughly 80% of the volume of the observable universe in the best-fit model. It has no boundaries, no edges, no walls. You could travel through it forever and never reach an end. But you would, if you traveled far enough, return to your starting point. And because of the identifications, the space creates an optical illusion on a cosmic scale. If you stood inside this space and looked outward, you would see what appeared to be an infinite expanse of galaxies stretching away in every direction. But it would be an illusion. You would be seeing the same finite collection of galaxies repeated over and over, their light reaching you by multiple paths that loop around through the topological identifications, like reflections in a cosmic hall of mirrors. In fact, you would see precisely 120 copies of the fundamental domain, tiling the apparent sphere of the sky. The proposal was captivating. Plato himself, 2,400 years earlier, had assigned the dodecahedron a cosmic role, writing cryptically that it was the shape the god used for arranging the constellations on the whole heaven. The idea that modern cosmology might resonate with an ancient philosophical intuition was irresistible. However, more precise data from the Planck satellite did not definitively confirm the dodecahedral model. The large-scale anomaly persisted, but it could not be conclusively attributed to a finite topology. The question remained open. And in 2024, a collaboration of cosmologists called COMPACT, the Collaboration for Observations, Models and Predictions of Anomalies and Cosmic Topology, published a paper making a provocative argument. They contended that previous claims to have ruled out non-trivial topologies were premature. Many exotic shapes, they argued, remained perfectly consistent with the observational data. The evidence against a finite, multiply-connected universe was much weaker than commonly assumed. The possibilities are staggering. The universe might be a three-dimensional torus with opposite faces of a cube identified. It might be a dodecahedral space. It might be something called a Klein bottle, a space so topologically strange that it has no distinct inside and outside. It might be any one of the 10 finite flat three-dimensional manifolds that mathematicians have cataloged, or any of the vastly more numerous curved and multiply-connected possibilities. In a multiply-connected universe, light could travel around the cosmos and return to its starting point. If you looked deep enough into space, you might see the same galaxy appearing in different locations in the sky, its light having reached you via different paths through the topological structure. You might even, in principle, observe our own Milky Way at an earlier epoch, its ancient light having circled the universe and returned to us. We have not detected such duplicated images, but that does not rule the possibility out. If the topology wraps around on a scale larger than the observable universe, the repetitions would lie beyond our horizon, forever hidden from view. The universe could be finite, but larger than what we can observe, and we would have no way of knowing. It is a humbling thought. The true size and shape of the cosmos might be fundamentally unknowable, not because we lack the technology to measure it, but because the speed of light and the finite age of the universe conspire to hide it from us. And there are even stranger possibilities lurking at the edges of theoretical physics. In the eternal inflation scenario, proposed by physicists like Andrei Linde and Alexander Vilenkin, Inflation does not end everywhere at the same time. Instead, it ends in local pockets, creating bubble universes, while the space between the bubbles continues inflating forever. Each bubble is a universe unto itself, potentially with its own geometry, its own topology, even its own fundamental constants of nature. Our observable universe would be one such bubble, floating in an endlessly expanding sea of inflating space, surrounded by an infinite number of other bubbles that we can never reach and never observe. In the many worlds interpretation of quantum mechanics, every quantum event spawns a branching point in the history of the universe, creating parallel realities in which every possible outcome is realized. If this interpretation is correct, then there are not just many universes but infinitely many, each one a slightly different version of our own, each one potentially with a different spatial topology. These ideas are speculative. They are at the frontier of physics, where rigorous mathematics begins to shade into philosophical speculation. We do not know whether the multiverse is real. We do not know whether other bubble universes exist. We may never know. But the fact that the mathematics of general relativity and quantum mechanics naturally gives rise to these possibilities is, at the very least, suggestive. The universe may be far larger, far stranger, and far more varied than the tiny patch we can observe. And so the question of the shape of the universe, which seemed so simple when Euclid first laid down his postulates, turns out to be one of the deepest and most open questions in all of science. We can measure the local geometry with extraordinary precision. We know the universe is flat, or very nearly so. But the global topology, the true shape of space on scales larger than we can see, remains an unsolved mystery. It is a question that connects the purest abstractions of mathematics to the most concrete measurements of observational astronomy. It is a question that has been asked for 2,300 years and is still, today, unanswered. And so, after 2,300 years of inquiry, from Euclid's quill pen in Alexandria to the cryogenic detectors of the Planck satellite orbiting 1,000,000 miles from Earth, where does the question stand? We know that the local geometry of the universe is flat, or so close to flat that no instrument we have built can detect the difference. The density parameter omega is measured to be 1, within a fraction of a percent. Parallel lines, as far as we can tell, stay parallel. The angles of cosmic triangles add to 180 degrees. Euclid, it seems, got the geometry right, at least on the scales we can observe. We know that this flatness is not a coincidence. It is a consequence of cosmic inflation, a brief, violent episode of exponential expansion in the first fraction of a second after the Big Bang, which stretched whatever initial curvature existed to the vanishing point. Inflation explains why the universe is flat in the same way that inflating a balloon explains why any small patch of its surface looks flat. We know that the universe is composed of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy, and that these components conspire to produce a total density almost exactly equal to the critical density. We know that dark energy is causing the expansion to accelerate, driving galaxies apart at an ever-increasing rate. And we know that geometry is not the end of the story. The topology of the universe, its global shape and connectivity, remains an open question. The universe might be infinite, an endless flat expanse, or it might be finite, wrapped around on itself in some exotic configuration, a cosmic hall of mirrors whose true extent lies beyond the horizon of our observations. each generation of thinkers believed they understood the shape of space. Euclid believed space was flat and infinite, governed by his 5 postulates, its properties self-evident and eternal. For 23 centuries, this was not merely a theory. It was a given. It was reality. Then Gauss, Bolyai, and Lobachevsky showed that other geometries were logically possible, shattering the Euclidean monopoly and opening the door to the unsettling idea that the shape of space might be a matter of empirical fact rather than logical necessity. Riemann showed that curvature could vary from point to point. That geometry was not a fixed backdrop, but a dynamic participant in the physical world. He gave us the mathematical language to describe spaces of any dimension and any curvature, a language so powerful and general that its full implications would not be realized for half a century. Einstein took that language and used it to build the most successful theory of gravity ever devised, showing that spacetime itself curves in response to matter and energy, and that gravity is not a force, but a consequence of geometry. Friedman showed that the geometry of the universe evolves over time, that the cosmos is not static, but expanding, and that the curvature of space depends on how much stuff the universe contains. His equations, dismissed by Einstein and ignored by most physicists during his lifetime, became the foundation of modern cosmology. Guth showed that a brief burst of exponential expansion in the earliest moments of the universe, cosmic inflation, could drive any initial curvature to undetectability, explaining the observed flatness of the cosmos. Penzias and Wilson discovered the cosmic microwave background, the echo of the Big Bang, and in doing so provided cosmologists with the most powerful tool for measuring the geometry of space. The teams behind COBE, Bohm ran G, WMAP, and Planck used that tool with ever-increasing precision, pinning down the curvature of the universe to within a fraction of a percent of flat. Perlmutter, Schmidt, and Rees discovered that the expansion of the universe is accelerating, driven by a mysterious dark energy that makes up roughly 2/3 of the cosmic energy budget, and whose very existence raises questions that nobody can yet answer. And the compact collaboration reminds us that even the seemingly definitive answer of flatness leaves the deepest question of all unanswered. The topology of the universe, its global shape and connectivity, which our current observations can constrain but cannot determine. The geometry of the universe is not just a topic in physics. It is a question about the nature of reality itself, about whether space is what it seems to be, or whether it harbors secrets that we have not yet learned to ask about whether the cosmos is simple or complex, finite or infinite, comprehensible or forever beyond our reach. Consider what it means that we can even ask this question. For most of Earth's 4.5 billion year history, there was no one here to ask it. For most of the 300,000 years that Homo sapiens has existed, we did not have the mathematical language to formulate it. For most of the 2,300 years since Euclid, we did not know that the question had more than one possible answer. And for most of the century since Friedman, we did not have the instruments to measure it. But now we do, and the answer we have found, a flat universe filled with dark energy, expanding forever into cold silence, is both profoundly satisfying and deeply mysterious. It closes some questions while opening others that are even more fundamental. What is dark energy? Why is the universe so precisely flat? What is the topology of space? Are there other universes with different geometries? These are not questions for the distant future. There are questions that experiments are being built right now, missions are being planned right now, theorems are being proved right now, which may help to answer. We do not yet have all the answers, but we have the tools, the curiosity, and the extraordinary mathematical language built up over millennia of human effort, from Euclid's axioms to Riemann's manifolds, to Einstein's field equations to the Planck satellite's data, to keep searching. And perhaps the most remarkable thing of all is this: that creatures made of atoms, living on a small rocky planet, orbiting an ordinary star in one of hundreds of billions of galaxies, have figured out how to ask what shape the universe is, and have gotten tantalizingly close to an answer. The universe may be flat, it may be curved, it may be something stranger than we have the words or the imagination to describe. But whatever it is, we are part of it, and the fact that we can hold the geometry of the cosmos in our minds, that we can trace the behavior of parallel lines across billions of light years, that we can listen to the echo of sound waves that rang through a plasma 13.8 billion years ago, and use them to measure the curvature of everything there is. That is itself a kind of wonder. Space may be flat, but the human story of discovering that flatness is anything but. You have been watching the entire history of the universe. If you enjoyed this journey through the geometry of space, make sure to hit that like button and subscribe to the channel. Leave us a comment and tell us what you think. Is the universe truly flat, or is something stranger waiting to be discovered? Thanks for watching, and we will see you next time.